Hello students, welcome to my channel iSmile Academy. Today we will be doing atoms and nuclei part 2. The first question, the energy required to remove an electron in hydrogen atom from n equal to 10 state is. So how much energy is required to remove an electron from the 10th state n equal to 10. So first of all we will write the equation for the energy. Okay, so this E n means the energy of the nth orbital. The energy possessed by an electron in the nth orbit is given by this relation minus 13.6 by n square. In our case n is equal to 10, so we find E10. So E10 is minus 13.6 divided by 10 square, which is actually 100. So what we have is minus 13.6 divided by 100. So if we divide 13.6 by 100, what we get is minus 0.0136. Now this is of course in terms of electron volt. So this much amount of energy is possessed by the electron in the 10th orbit. So we must supply an energy which is in the positive sense. So the answer in this case is D, plus 0.0136 electron volt. Next we come to question number 2. The kinetic energy of the electron in an orbit of radius r in hydrogen atom is. So we need to find the expression of kinetic energy in terms of E and R, because in the options that is given. Now see, for an atom, okay, this is the nucleus, okay, this is the nucleus, and the electron is revolving around this nucleus in a circular orbit according to Bohr's theory. So this is the electron, and inside there is here we have proton. So there is a force of attraction between the electron and proton, and it is called as the electrostatic force of attraction. Now this electron is revolving in a circular orbit, so it has some centripetal force. So this centripetal force is provided by the electrostatic force of attraction between the proton and the electron. So how do we write here? I am just writing the short form. So this CF means centripetal force which is moving the electron. It is provided by the electrostatic force of attraction between the electron and the proton. How do we add centripetal force? Centripetal force is actually mv square upon r, and electrostatic force is given by 1 upon 4 pi epsilon 0. I just write E square upon r square. Okay, now since this term 1/4 pi epsilon 0 is a constant, so we can directly write this as k times E square upon r square. Now I just shift this r here. Okay, now we are not considering this equation. Okay, now we are comparing the first and the last because both are same. So I am shifting this r here, and here there is r square, and here we have r. So what we get finally is one r gets cancelled, and here we have mv square is equal to k E square upon r. It is r, it's not r square, because r has already got cancelled out. Okay, so what we have in this case is k E square upon r. Now mv square, we multiply both the sides by half, so what we get is half mv square is equal to half k E square upon r. Okay, so here what we observe is which is equal to k E square upon 2r. Okay, so this is the what we have. Now this half mv square means the kinetic energy. Okay, so kinetic energy is k E square upon 2r. So this option is correct, E square upon 2r. Okay, with the given. Next we come to question number 3. The ionization potential of hydrogen atom is 13.6 electron volt. Hydrogen atoms in the ground state are excited by monochromatic radiation of photon energy 12.1 electron volt. The spectral lines emitted by hydrogen according to Bohr's theory will be. Okay, so 13.6, it is the amount of energy if this potential is given to the electron, it can just come out of the hydrogen atom, but we are providing energy of 12.1. Okay, so what we will find first, by providing 12.1 electron volt, how much the electron will get excited. Okay, to which orbit can it get excited. So first of all, we see the difference between the two energy, that is 13.6 minus 12.1. it is around 1.5 electron volt. Okay, this is difference 1.5 electron volt. So then what we see for a hydrogen atom, okay, when n equal to 1, the energy possessed is minus 13.6 divided by 1 square, which is minus 13.6 itself. For the second shell, okay, for second shell, n equal to 2, for n equal to 2, the energy possessed is minus 13.6 divided by 2 square, which is 4, which is if we calculate it, what we get is 3.4 electron volt. So this is 3.4. okay, then for n equal to 3, okay, for n equal to 3, what we have, it is minus 13.6 divided by 9, which is actually 1.5. okay, now the difference is 1.5. so if this much 12.1 volt electron volt is provided by some external source, the electron which is in this shell, okay, I will just draw with another marker, the electron, that is this electron, this electron would get excited and jump to n equal to 3. okay, now after excited, it may come down. okay, now what we want to find, how much spectral lines will be emitted by that atom, by that atom, due to this jumping, with the electron coming down. So now here, what n is equal to 3, okay, what the formula says, the number of spectral lines emitted, okay, number of spectral lines is equal to n into n minus 1 divided by 2. This is the formula for finding this. If n is 4, we have to apply any formula. We must first find n. So n is, we got n as 3. okay, so 3 into 3 minus 1 is 2 divided by 2. 3 to the 6, so answer is 3. So 3 to the 6 divided by 2 is 3. So this, in this case, the answer is 3. We will get 3 lines. okay, you can, it is of course evident from this, the electron may jump from here to here 1, from here to here 2, and it comes here, it comes again, jumps down here. So these are the 3 lines. okay, although it is not asked, but we must know how, what are the 3 lines are. okay, next we come to question number 4. The ratio of the energies of the hydrogen atom in its first to second excited state is, okay, we want to find the ratio of the E1 upon E2. okay, we have this expression En, we have this En is equal to minus 13.6 upon n square. okay, so for E1, what we have for E1, we would have equal to minus 13.6 upon 1 square is for same 1 itself. okay, and for E2, it is minus 13.6 upon 2 square, which is 4. okay, so what is then E1 upon E2? So E1 upon E2 would be equal to minus 13.6 upon 1 upon minus 13.6 divided by 4. This is actually 2, this 2 square is 4. So what we get is E1 upon E2 is actually 4 upon 1, which is actually 4. okay, so the ratio of first to second excited state is actually 4. actually 4 is to 1, answer is 4. So this is the answer. Next we come to question number 5. The ionization potential of hydrogen atom is 13.6 electron volt. The energy required to remove an electron in the n equal to 2 state of the hydrogen atom is, so ionization potential means the amount of energy required for to remove the electron from the from the first shell itself. okay, 13.6 is required. okay, so now this energy, okay, E2, for the case of hydrogen atom, for E2, okay, we have the energy possessed by is minus 13.6. we have already seen this is divided by 4. okay, 2 square is 4, so this comes out to be around minus 3.4 3.4 electron volt. This much energy is possessed by the electron in the second shell. So if we supply plus 3.4, then so this much amount of energy is required to remove the electron from the second shell. Okay, so answer is 3.4. Then the electron possesses minus 3.4 electron volt, so we must supply at least 3.4 plus 3.4 electron volt so that it becomes free. So the answer in this case is 3.4 electron volt. Next is question number 6. A beam of fast moving alpha particles were directed towards a thin film of gold. The parts A dash, B dash, C dash of the transmitted and reflected beams corresponding to incident parts A, B, C of the beam are shown. So the number of alpha particles, so which are maximum, which are minimum. Now this is evident from this figure. You can see this B, okay, the B beam which is incident, it is reflected the most. It is almost reflected by an angle of 180 degree. The A, it is almost as good as undeflected, and C is deflected but not by a large angle. Okay, so we conclude that in this case B A dash, okay, so here number of particles A dash will be minimum and B dash will be maximum, because B dash is deflected by almost 180 degree, okay, by a larger angle, and A dash is almost undeflected, so it has minimum and minimum number of alpha particles. Okay. So the answer in this case is C. Okay, the answer is C. This is the answer. Next we come to question number 7. The radius of electron's second stationary orbit in Bohr's atom is r. The radius of third orbit will be. So for the case of Bohr's orbit, okay, this r, radius of the orbit, nth orbit, is proportional to n square. Okay, so we can write it Rn equal to some k times n square. Okay, so for the given case, what we have, R2 would be equal to k times n, means n is 2, so it becomes 4. But what we are given is it is equal to capital R. Okay, R2 is capital R. So what is R? R equal to k4. So k is equal to R by 4. Now what we are interested in finding R3. Okay, so what R3 would be equal to? K into 9, because n square, because n is 3, so it becomes 9. So R3 is k9, but k equal to R4, R by 4. So R3 would be R upon 4 into 9. Okay, so in the given answer, we will solve this 9 by 4. Okay, so 9 by, if we divide 9 by 4, what we have is 2.25 times R. So this is the answer if we solve it. Okay, next we come to question number 8. In any Bohr orbit of hydrogen atom, the ratio of kinetic energy to potential energy of electron is. So we are given some options. So let us see how we write the expression for the kinetic energy. So kinetic energy, Ke, is given by the expression K Z E square upon 2R, and potential energy is minus K Z E square upon R. So K is a constant. There are some terms we are just putting him as a K constant. Z is the atomic number, E is the charge, R is the radius. So now we want to compare kinetic energy with potential energy. So Ke upon Pe, the potential energy. So this is Kz E square upon 2R upon minus K Z E square upon R. So here we see there are many common terms which would of course get cancelled out. So here we see this K cancel out, this Z E square, this E square, this R and this R. So what we are left is minus So here we are getting 1 upon 2, and here there is just 1, so we get 1 upon 2. So this is the answer. C is the answer for this particular problem. Okay. Next, number 9. The ratio of the kinetic energy to the total energy of an electron in a Bohr orbit is. So first of all, we write the expression for the kinetic energy. Okay, we already wrote in the previous case. So kinetic energy is equal to k z e square upon 2r, while total energy Te is equal to minus k z e square upon 2r. So we need to find the ratio of Ke versus Te. So this is, we write first K, kinetic energy expression. This is the kinetic energy expression upon 2r upon minus K z e square upon 2r. Now both in both the case, what we see, both all the terms are same. Okay, so this entire expression cancels out with this one, and we are left with 1 upon 1, which is actually 1. We don't write this negative sign, so only option left is this one. Okay, so 1 is the answer for this case. Okay, so next we come to question number 10, the last one of this session. When a hydrogen atom is raised from a ground state to an excited state, what happens to the potential and the kinetic energy? So see here, this is, suppose, let us, this is the nucleus, this is the maybe the first state, then we have the second, and so on. Okay, so we have various energy levels. Okay, so what happens when electrons goes from one level to another level, excited level, lower level to higher level, what happens to the potential and the kinetic energy? So we know this kinetic energy is proportional to 1 upon r. Okay, and potential energy is proportional to minus 1 upon r. Okay, so as the electron goes to a excited state, the radius increases. As in case of, what happens in case of kinetic energy? In case of kinetic energy, as r increases, kinetic energy decreases. But in case of potential energy, as r increases, the potential energy also increases, because there is a negative sign. Okay, so in this case, what happens? Potential energy increases and kinetic energy decreases. So first option A is correct. So students, that's all for today's session. Okay, all the best. Thanks for watching.